Kia ora koutou. Welcome to this inaugural lecture from Professor Graham Donovan. So it's my great pleasure as Head of Maths to welcome Graham into the professoriate. I know that he's already been enjoying very much attending Senate meetings, which is the enormous privilege that comes with this position. It's my great pleasure to, I'm going to let Graham introduce himself. He's been a member of the department for a long time and he's an absolute asset to the place, and I'm very pleased he's been promoted to professor. So put your hands together for Graham.
Thank you very much, Stephen. Thank you all for coming. I'm very happy to see you all here. I wanted this being an inaugural lecture to start out with newspaper clippings of me as a child, ideally doing mathematics somewhere. There were math contests and all this sort of thing. So I went back through the archives because they're all available online now. I thought, okay, well, I'll see what I can find. I remember various things, but I don't know what was in the paper. And I didn't find exactly what I was looking for, but I found a variety of things, and I think they're actually more informative than what I was looking for when I started. So I grew up in a small town in the western United States called Walla Walla, Washington. And this is the amazing newspaper there, the Walla Walla Union Bulletin. And I went searching through their archives for what I could find. And I found some articles like this, 5 paragraphs about the math team that went to the state competition. Then I found things like this, which is a longer article complaining, letter to the editor, complaining about the article from somebody involved. I believe this is, in fact, longer than that, but there you go. And I did eventually find the full-page photo, all the rest of it involving me. Nothing to do with mathematics, but my amazing skills, apparently, at carving pumpkins, thematic for Halloween. So there you go. I don't know what amazing talents I have, but there I am, aged whatever it is, 12 or 13. I can't read it from here. So I think that tells you most about the town that I grew up in. So I went on from there to the University of Washington to do a degree in mathematics. For a time, mathematics and physics before I saw the error of my ways, and then mathematics and computer science before I saw the error of my ways again. And then the University of Washington being one of these places where the mathematicians and the applied mathematicians are unfortunately not on speaking terms. I eventually discovered the applied math department that the mathematicians have been hiding from me. So I went on to do my PhD at Northwestern in applied mathematics. And for those of you who might be confused about the names of the geography, Washington is this one up here, Washington State. It's not this one over here where all the really crazy stuff happens. And Northwestern is here outside of Chicago. What it is that's northwest of, you can decide for yourself. Anyhow. Okay. So I imagine a lot of you know the website, the Mathematics Genealogy Project. I'm not sure it exists in all disciplines, so some of you will have seen it and some won't. And I want to show it because it's fun. So this is my page, PhD 2008. Advisor Bill Kath. So you click on Bill, and I put up a picture of Bill. He was my PhD supervisor at Northwestern. I shouldn't think too many of you know Bill. Keep clicking, keep going back, because that's fun. You start to get some names that some people will know. I'm sure Don Cohen and Joe Keller are definitely both known to James, at least, if not other people. Okay. Courant, as in the Institute at NYU. Hilbert, as in the space. Klein, as in the bottle. Lipschitz, as in the condition. Dirichlet, I don't know. Get all the choices you want. What do you want for that? Okay. Poisson, Fourier, Laplace, Lagrange. And rather interestingly, if you go and explore yourself and your friends, there only seem to be sort of a handful of lineages that end up back at a very small number of places. So it's quite fun. I don't know if this exists in other areas for, I don't know, statistics or what have you, but I think it's quite enjoyable. Anyone with sharp eyes who's been paying attention might have noticed another name which is familiar down here. So there's no chance that I shall ever be, I think, Bill's most famous student, because Nathan Kutz has probably got that sewn up in spades. He's one of these people who isn't happy to just get 10,000 citations a year. He's got to have similar numbers of YouTube followers and all the rest of it. So anyway, I can claim him as my academic brother and try to bask in some reflected glory, but that's about it. Okay. So in 2008, I finished my PhD, and I came to New Zealand to do a postdoc with Maren Tawhai and James Sneed. Maren, of course, is the director of the ABI these days. So when you go to Maren's website, you find a lovely picture of Maren that I can put on my slides. And then when you go to James's website, you find this. And it's your own fault, James. And then I thought, I can't put this picture of James in my thing. I've got to have a slide. So I go James Sneed Auckland, and I do Google image search, and I find this, which he's probably forgotten about. But I found it both because it's such a wonderful piece of New Zealand Herald journalism, but I also like the sort of symmetry here. We've got James Sneed, age 44, professor of applied mathematics at the University of Auckland. So it happens that my 44th birthday was a few months ago, so I feel a certain symmetry with this, this article as I read it and thought about James being James. Okay. And then in end of 2010, beginning of 2011, I was lucky enough to decamp from that postdoc at the ABI and move down as a lecturer in mathematics. All right. So this is a tiny conference that none of you have ever heard of that I went to in 2015. And despite being a tiny conference that none of you have ever heard of, it's sort of an important waypoint in what I want to tell you about in a variety of ways. Okay. The first thing is that I can't believe I went to it at all, because the 25th, 26th of March 2015 was not a good time to be traveling, because Alice was 2 months old and Luke had just turned 2. So Claire deserves a lot of credit for my having gone to this conference at all, I think. The second is that this was the first time I met Peter Noble in person. Peter and I have now been collaborators for about 15 years and have, I think, successfully published a couple of dozen papers between us. So the fact that he and I first met there and began collaborating was something that was certainly noteworthy. The other thing that happened here, and the real reason that I brought it up, is something that almost sort of happened in passing. So I have to tell you a little bit about this conference first. So it's about 40 or 50 people. It's really small, it's really focused, and it's really interdisciplinary. Physiologists, biomedical engineers, medical doctors, sort of a quantitative end of respiratory physiology. It's organized quite irregularly every 2 or 3 years when one of the 40 or 50 people can take on the job and get everybody out there. It's a wonderful meeting, and it's not like this, right? It's not people standing in front and lecturing and blah, 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 blah. It is a little bit of presentation and a lot of discussion in very free form. And so something happened at this meeting that I remember very distinctly and that has sort of shaped my thinking over time. And what was happening is we were having a discussion, was being led by a physiologist, and there was a lot of other chatter in the room. And they were discussing a paper that had been published recently. And what they said about the paper was, it claims to address a topic that they were all interested in, but I tried to read this paper, but it was written by a mathematician. And what they meant by that was that they couldn't understand a word of it, right? And it's the message, the findings of this paper were just completely lost on this community. And it wasn't an isolated sentiment, right? The person who said this, and everybody else kind of went, yeah, okay, I got it, yeah, we couldn't understand it. And so this was sort of a, I don't know, not wake-up call, but I was one of either 1 or 2 mathematicians in the room at the time, and I strongly expect the speaker was not aware of the fact that I was a mathematician in the room when this was said, but nonetheless, it sort of got me thinking about why it was that the work of this other person, it could have been my paper, but it wasn't, was so inaccessible. Okay? So I'm interested in some questions following on from this, including myself, as to why we as a community, as mathematicians, are often not particularly good at communicating in this way. And I think that there are issues of language and philosophy and style that come into this. Okay. So for example, let's start with a simple word, which is proof. That's right. It's a really simple English word. And as mathematicians, we use it in a very specific way. We have a very rigorous meaning of this formal logical construct of following on from one thing to the other. And elsewhere in empirical science, it just doesn't mean that at all, right? It's just accumulated evidence. And so we use these words in different ways, and we think about things in different ways. And we can probably talk about having hypotheses and maybe conjecture, but these mathematical concepts of proof and theorem and lemma and all the rest just don't have analogs in empirical science, right? Those concepts just aren't meaningful. And that doesn't say that they aren't meaningful full stop, but it's just that we're speaking a different language. Similarly, a lot of the interaction between mathematics and biology has to be predicated on thinking about models. So you'll all be familiar with theoretical models. We might think about mathematical models or conceptual models. They're going to have assumptions, which ideally are explicit, but are oftentimes left implicit. And I can promise you, from having talked to a number of people over a number of years, that there is definitely a certain branch of biology and physiology, at least, to whom the vast majority of theoretical models are not real, and they're therefore suspect in some way. Okay? There are, on the other hand, experimental models. You can have animal models, or ex vivo, or cell culture, or blah, 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 all sorts of different assumptions. They also have assumptions, implicit or explicit. And to a certain segment of science, these are somehow intrinsically more valuable because they are real rather than not. And like all things, there's kind of a kernel of truth here. There's probably more scope to get your theoretical models wrong, just because you can do things wrong in an essentially unlimited number of ways, right? So you can go really, really wrong. But I would sort of take issue with the idea that one of these is intrinsically more valuable than the other because they are both models. They both need to be done carefully and can be made valuable in certain situations and misleading in others. But what I think is important is that some of this feeling about the non-realness of theoretical models is partly to do with the way we as mathematical biologists or modelers present our work, and partly our fault. So what is mathematical biology then? I think that most people's ideal situation would look something like this. You start with some question in biology, which is interesting, biological in question, right? That neatly inspires some new mathematics, and the new mathematical insight leads to some biological understanding. It's great. Everybody should do this. Everybody wins. What's not to like, right? It's wonderful. Okay. But in my experience, the picture looks a little bit more like this, right? Biological questions do inspire new mathematics, and that's great. We love new mathematics. I'm a mathematician. We're doing new mathematics. That's worth doing, right? It's wonderful. Sometimes the biological question can be addressed by existing mathematics, and that leads to the biological understanding. And that's great too. Maybe you're not doing mathematics anymore, maybe you're doing biology, but that's valuable in and of itself. Okay? And so my contention is that we shouldn't view this as being less valuable, but we need to recognize that it's different from the first picture, right? Which is that we need to recognize what it is that we have accomplished and who cares about it. In this first one, biological question, new mathematics, that's great, wonderful, but that doesn't mean that it then has intrinsic relevance to the biologists who gave you the question in the first place, right? You can go back to them and say, I found this amazing, interesting thing, and it's great, curiosity-driven research, I love it, let's do it. But it doesn't mean that it's relevant to the problem that you started with. And in order to parse that difference, you have to know what it is that really inspired this question, what really is the central question, and what you have really demonstrated. And so my contention that we have partly brought this distrust of models on ourselves is that too often we, myself included, do this and then think, oh, there must be some biological understanding that's arisen from this interesting mathematical thing that I found. Sometimes yes, sometimes no, but not intrinsically in and of itself. Okay. And the final thing is a little bit more ticklish. As mathematicians, we have an unfortunate tendency to treat complexity as a proxy for value and not really prioritize making what we do accessible, right? We see a lot of, I do hard stuff and I'm gonna give this talk and only a small fraction of my audience is gonna understand it. And it's just kind of the, I don't know, milieu of mathematics. It's the way we do it. And it's not the best way to communicate these results, especially across disciplines. Okay. Okay. So I would like to tell you sort of the story of bronchial thermoplasty and my involvement in it. So in order to do that, I need to take you back to asthma and how it was treated and what was understood about it in about 2008. So there are a couple of important processes in asthma, right? There's absolutely inflammation and mucus secretion, i.e. your airways are inflamed and they're filled with mucus. These are not good for breathing. That's easy to understand. You also, some of you will know, and many of you probably do not, that you've got a band of smooth muscle wrapped around your airways. Why that is there, nobody really knows. There are some theories. But what's definitely true is when that switches on, it starts to narrow your airways, and this is also bad for breathing in the obvious way. So in about 2008, something like 95% of therapies could be controlled by, of cases could be controlled by relatively standard inhaler therapies, which is just exactly what you think of, people taking their inhalers. And what was not obvious to me when I started working in this, and is maybe not obvious to you, is that there's pretty serious mortality and morbidity where these standard therapies failed. So I definitely remember reading this paper in about 2008 or 2009. I don't know how well you can see it. I can't even find right now the paper that it came from, but I clipped it out before. It's very simple. Subject demographics and clinical details. Highlighted the cause of death. Asthma attack, age 23. Asthma attack, age 10. Asthma attack, age 10. Right? It's not just kids wheezing on the playground and, oh gosh, I forgot my inhaler and I better go get it. Right? There's this very serious residual, hard to treat, severe asthma, where it's not just the sort of relatively mild and treatable disease that I was thinking of when I started working in this area. So in this environment, for a number of years, a number of groups, including myself, were interested in studying the spatial patterns or the ventilation heterogeneity, what the physiologists call clustered ventilation defects in asthma. So these are some experimental images, just to sort of give you a rough idea of what we're talking about. This is your, a slice through here, ventilation in your lungs. If you are sitting here breathing quite normally, you have a relatively homogeneous distribution, probably like this. And in severe asthma, you start to get things more like this, where you have these big regions where the ventilation is just completely gone, big black areas, complete ventilation defects. And also these areas of hyperventilation to counteract the hypoventilation. And there was a lot of interest in how these emerged and how to model it and how to understand them and what it told us about the underlying pathophysiology of asthma. This paper came out in 2007 in Nature and really kind of launched the modeling of this as a dynamic emergent phenomena. And there have been some follow-on models from my group and others where we've been looking at sort of the pattern-forming aspects of this, how these ventilation patterns emerge, how the symmetry breaks, et cetera, et cetera, et cetera. Okay. So there are interesting both mathematical and biological questions here, but they're not exactly the same questions. So the biological questions, the physiological questions, the medical questions are along the lines of what are the primary drivers of these ventilation defects? To what extent do they persist over time and recur? And how do the answers to those two questions interact with one another? Okay. And the sort of related mathematical questions are to do with how stochasticity or randomness, time, and spatial structure interact in order to generate these sorts of patterns. So I want to, at the risk of oversimplifying quite a lot, give you a sort of really crude, I hesitate to even use the word model, but example of what I mean by the interaction of these processes. So let's imagine we're flipping coins, and we've got a big grid of these. These are done by ChatGPT, of course, which is why they're sort of strangely deformed in a variety of ways, right? Okay, so we've got a big grid of coins, right? They're fair coins. We toss each of them, and we look at the distribution of what we have here. And what we have is nothing interesting, right? We've got, on average, 50% heads, and we've got 50% tails, and we have no structure as to where one or the other lies. So now let's change our game and imagine a situation in which the probability, when we retoss a coin, of coming up heads, say, depends on how many heads sit near to it. Okay? So we have a dependence from one coin to the next by sort of local contact, nearest neighbor like this. But we're still going to keep this to be fair, averaged across all the coins. So these are all fair, uncoupled coins, and it's being tossed and tossed and retossed and blah, 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 right? And you're 50% heads and you're 50% tails, and nothing interesting is happening at all. And as we start to change away from the situation of the uncoupled coins to those that are coupled, so you're depending on your nearest neighbors, then what you can do is you can start to generate these sorts of spatial patterns, right? If you have heads that want to be near heads and tails that want to be near tails, but everything has to stay fair on average, then you're going to start to form these coherent structures. And of course, you can go back and make everything unbiased, and you can have a different pattern, and you can go back and everything make it unbiased, and you can have a different pattern, and you can go back, and you can have a different pattern. There's no systematic reason that you should have heads in one place or tails in one place in this particular model, but you have the emergence of these clustered structures. What's perhaps less obvious is that there's also some dependence of time. If I do this quickly, I can get these small structures, different small structures. If we instead advance this much more slowly, right, it's possible that we can generate these much larger scale structures, right? So the size of the patterns that we generated are not just down to the coupling and the structure, but also to the time scale of how we force these to evolve. And so these are the kinds of questions that we're interested in an oversimplified fashion. Now, of course, the problem that I'm interested in is not coins on a lattice, but we're talking about lungs and airways. And this is a sort of classic cast of the airway structure. So you've got the trachea here and the main bronchi branching and branching and branching. This is an actual cast, quite a famous one. If you start to think about the interrelationships of the airways here, you begin to realize that there are multiple ways in which things are interconnected. There's the obvious one, which is that you have the branching tree structure. So if you think about a daughter airway and a mother airway, then you obviously have flow through these tubes and everything's coupled that way. The additional things are that, of course, what happens is once the air flows through all of your conducting airways, it comes out into the spongy bit. It's called the parenchyma, where the gas exchange happens. And that's more or less like a sponge in which all of your airways are embedded, and the mechanical properties of your airways depend on what's going on in that parenchyma. So by inflating this tissue, we have additional relationships between all of these airways, and they are coupled in sort of different ways. And so we have to start to think about not just coupling along the tree, but off the tree in various different relationships. And so the kinds of questions we're interested in is the recurrence of patterns, not in a coin tossing game, but in these tree structures. Okay. So these were the problems that I was interested in at the time. And into this situation enters this treatment for asthma called bronchiothermoplasty. So I motivated for you the idea that there was this small residual cohort of asthma sufferers for whom the standard therapies failed. And bronchiothermoplasty, which was a treatment which was developed to address this hard-to-treat group. It's very different. It's not an inhaler at all. What's the technical way of saying it? Direct targeting of airway smooth muscle via bronchoscope and radiofrequency catheter. What does all that mean? Well, it means they take a wire and they put it down your trachea and they stuff it into your airways as far as it can go, and then they heat it up to about 55 or 60 degrees C. And the idea is that temperature is very carefully calibrated to destroy the capacity of the smooth muscle to contract without doing too much damage to the rest of the tissue while they're at it. Sounds horrible, doesn't it? Yep. Okay. And the sort of obvious thing, right, is that, if you go back to I won't back to my cast, you have something like 30,000 conducting airways in each lung. When you're doing a direct mechanical treatment like this with a catheter, which is a couple of mil across, you're going to reach 30 of the large ones, if you're lucky. So you're treating a small number of relatively large airways. And for a variety of reasons, bronchiothermoplasty was fairly controversial from inception. So there were a variety of clinical trials, and I don't want to get too far into the weeds with this, but essentially the results across many clinical trials were that a variety of soft measures, which is to say things that patients report, like questionnaire scores, how they feel, how often you turn up at ED, that sort of thing, those all improved. And various hard measures, which are essentially how well do you blow into a tube, those don't. And so the conclusion of many at about this time was, well, it's just placebo, right? The patients, they've had a treatment, so they think they feel better, so they give you better scores on the questionnaire. And there's nothing going on physiologically, right? There's a total placebo effect. And so the people who were after this, they went and did a sham-controlled trial, which means that they had a control group that actually went under anesthesia and had a bronchoscopy. They just didn't get to press the button to turn on the heat, right? They had all the rest of it. So they thought they had had the treatment, and they got the same answers basically, but the attitude in the sort of relevant scientific community was that somehow, despite the sham-controlled trial, it was still the placebo effect. And definitely part of this was around the uncertainty about the mechanism of action, because there were definitely questions about how treating such a small number of airways could be effective. Okay, so it was approved for treatment in the US in 2010, and in Australia a few years later, and I don't think it's ever actually come to New Zealand, but anyhow, despite all this approval and the fact that it got rolled out, it continued to be controversial. There were letters to the editor and all sorts of criticism of the trial designs and blah, 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 and all sorts of mucking. And the sort of bottom line was probably something like this. The true mechanism of a clinically important benefit of bronchiothermoplasty is yet as unknown. And so at this time, this was definitely the received wisdom in sort of across the scientific community in this area, except for a relatively small number of evangelists for BT, for bronchiothermoplasty. And into this waded Peter Noble again. So I told you how I met Pete in Sydney in 2015, and we've been working a lot since. In about 2017, he said to me, Graham, we've been working on all this patterns of ventilation and what's going on in asthma and how are these ventilation defects emerging. What do you think is going on with thermoplasty? And I said to Pete, don't be silly. Everybody knows BT is just placebo effect. It doesn't do anything. And he said, well, just look. The model we've been building is basically perfect for this. We've got the smooth muscle. All we have to do is reduce it in the treated airways. Look at the ventilation patterns. Okay, Pete. Okay, fine. We'll look. Okay, so Pete was right. We went and we looked. We treated this small number of airways, which everybody thought wouldn't be enough, right? And lo and behold, we found that the ventilation patterns in our simulated severe asthma subjects were shifting from sort of severely heterogeneous to less so, right? In a systematic way. And this wasn't something that could be particularly well measured at the time, but it came out quite clearly out of the model as we were building at that time. And the advantage of having a model is that we could dig into it as much as we like to figure out what was going on. And the bottom line was that what we found was that thermoplasty was improving ventilation heterogeneity, but only under relatively severe conditions. So you needed the muscle to be activated up to a certain degree, i.e. when the patient is not very happy. And in that situation, they're not as bad as they would have been otherwise. And this was an important result because it makes it really hard to pick up with these traditional clinical function tests, because when you've got a patient in the clinic and they're struggling to breathe, you don't put them on the machine to measure their flow, you treat them, right? So you would expect that these are going to be very difficult to pick up with traditional clinical function tests, but they're still going to manifest in the soft measures because they're going to feel better and they're going to turn up in ED less often. Okay. And so we published this in the Red Journal, which is a good journal in physiology. In the sort of spirit of my talking later, this paper itself doesn't have any mathematics in it at all, really, because we've written it to try to be accessible to the audience that we want, which is that these physiologists. But it is written on all sorts of stuff written by a mathematician, i.e. me, right? So unintelligible to those people. All right. So that was 2018. Fast forward to 2025. What do we know? We know that the soft measures continue to persist at 10 and even 15 years now. It's getting to be a long time for the placebo effect. Moreover, imaging has come along a lot of ways. So we can now see that thermoplasty improves ventilation heterogeneity as measured by matched CT functional respiratory imaging, they call it. Hyperpolarized either helium or xenon MRI, or another technique called pre-fill MRI. It doesn't matter the details of these so much, other than they all show that the airways are dilating on CT and the ventilation heterogeneity is improving by these other measures in basically the ways that we predicted. So Pete was really right and I was really wrong. Despite all of that, bronchothermoplasty is now all but dead. It's been withdrawn for commercial reasons. Part of this is that the controversy around the mechanism of action was either never resolved or was resolved too late, but that would be oversimplifying quite a lot because the advent of monoclonal therapies over the past 10 years has changed asthma treatment completely. So I don't necessarily want to say that, you know, BT was the answer, but what I do think is that we missed something, right? Everybody, including me, said, this isn't doing anything. It's completely placebo, and we missed it. So what did we miss? And what should we take away from that? Right. So sort of narrowly with the story of BT, I think the main thing is an over-reliance on traditional measurements and the desire to have a single gold standard measurement of lung function, which makes life really simple. Everybody wants to have one. We want to have the one measurement that measures the one thing, and then we give them the treatment, and then we see whether the one things change, and we don't have to do any fancy statistics, we just check, right? It works or it doesn't. Well, life isn't that simple. We've got all sorts. We've got multiple complex measurements that have to be synthesized in different ways, okay? Imaging definitely plays an important role, and I think even though BT is gone and it's not coming back, this has lessons for how we want to be assessing future therapies so that we don't make the same mistakes that we made before. Okay. More broadly, I want to emphasize that scientific communication is hard, especially across disciplines. And the first thing you have to do is to get deeply enough into the area that you're working in order to understand what it is that your audience understands and cares about. And this is not easy, it's hard work, but it's something that we need to do. And in my view, it's something that we need to do better, especially in this era where we're concerned about everything needing to be commercializable, and the threats to basic research and inquiry-driven and all the rest of it, that's all great. And we're not doing ourselves any favor by keeping people from understanding what it is that we're doing and what its benefits are. Okay. And if you don't believe me, then you can believe Terry. Okay. So for those who don't know Terence Tao, he's probably the most famous living mathematician. Can we do that by straw poll, maybe? Yeah. Okay. So what does he say? Right? It may feel like you've attained some level of intellectual achievement if you can discuss a topic which is so difficult or jargon heavy that most of your audience do not understand what you were talking about. Yeah, we've all been in that talk, right? Okay? But it's a far greater intellectual achievement to actually explain that. Right? And so this is something that has, increasingly influenced my thinking, right? We treat complexity as a proxy for value, and it's a poor proxy for value. And we shouldn't do this. That's my take. Okay. When did we actually start, Stephen? 20, 30, 35 minutes? Okay, yeah. I shan't be too long. So we'll just tell you a little bit about where this is going with some of my work more recently. So what we're now thinking about is in an area variously called critical transitions or tipping points or regime shifts or catastrophic shifts or blah, 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 blah. Everybody sort of has the popular science idea of a tipping point where you imagine ecosystem collapse or ice sheet collapse or various doom and gloom in the environment. And the typical picture is you have something like this where you have temperature, for example, bouncing along in a happy place, and something really bad happens, and now you're all dead. Okay? This can happen in multivariate, and what we're really interested in is also in spatiotemporal systems where the changes that occur over time are not just in a scalar variable or in a low-dimensional setting, but happen in some spatially structured way. And in particular, we believe that these exacerbations of asthma go through these spatially structured transitions over time. Now, this imaging technology doesn't allow for you to verify that in any direct way because this is hard. Patients have had 3 of these ever, much less in any longitudinal sense. But that's where we think the evidence is taking us. And so in the one-dimensional setting, where you're just thinking about temperature, for example, you can imagine a system which is very simple like this. You have an energy landscape, and you've got a ball bouncing around in this energy landscape, in this potential, which is being perturbed by noise, and it's bouncing around. So when we are sitting in this potential wall, we're setting up in this high observable state, and everything is okay. And one thing that can happen, right, is that we can have just a big enough noise kick that takes us over this barrier into the other potential, and we're going to go through some sort of transition down to the other state. This can happen in a couple of different ways. It can happen in this sort of way where there's no change to the underlying energy landscape and you just get kicked from one potential well to the other. Or it can happen in these situations where the underlying energy landscape of the system is changing at the same time. Where, for example, you have just the one basin of attraction where you're sitting and everything is happy. And you move into a regime where you have the 2 coexisting basins, and noise might or might not push you over. And eventually you end up in a further transition where only this low observable state exists. And what's important is this phenomenon has been known for a long time. The physicists started calling it critical slowing down in the 70s. And the idea is that if this is happening, then there's going to be a characteristic signal in this time series, for example, in the autocorrelation, where the return time is going to start to increase as this basin flattens, and you're going to be able to see that as an early warning signal of this transition approaching. And depending on the kind of transition you have, you might get one, or you might not, or you might have to have different early warning signals. And so what we are interested in is these critical transitions in asthma, as asthma exacerbations as being these critical transitions. There is some clinical evidence for this. So this is a study that was done by some colleagues in Australia. And I've relabeled these to try to make them a little bit easier for you to do. So this is like a symptom score. So this is how the patients are reporting that they are feeling. And these are flow measurements, which is what's being measured at the mouth as they blow into a tube once a day. And day 0 here, everybody's been scaled. So day 0 is where the doctor has diagnosed an exacerbation. So what's important about this is that the differences, the increases in the symptom score, right, start 1 day before the diagnosis, when they actually get into the doctor and he says, yep, you've got it, okay? But the measurements in the particular kind of flow measurement, right, popped up 4 days before. So it's not a huge amount of lead time, but it's an amount of lead time that you might be able to exploit in terms of changing therapies, so forth and so on. So there's definitely some evidence that early warning signals might exist in this context, thinking of exacerbations in asthma as critical transitions. All right. Where we really want to go with this, eventually, is to be able to not just take that scalar measurement at the mouth or fairly low dimensional measurement at the mouth, but we'd love to be able to have these pictures of what's going on with the ventilation distribution with a much higher time resolution to be able to see this longitudinally. So Pete and company in Perth have been working on using developing an EIT system to do this. This is an early prototype system where you get your electrodes stuck on, but the idea is that eventually you'll have a belt that you can just clip on that's got the things indoded. You press the button, take a picture, see what your ventilation distribution looks like. It doesn't have anything like the spatial resolution of the better techniques, but the ability to do it longitudinally and in a home monitoring setting is sort of potentially a completely different regime from what has existed before. And the hope is that this can sort of be a test case for spatiotemporal EWS if we can see the changes in these ventilation distributions in this way. The sort of classic areas of climate and ecosystem and ecology are not particularly data rich because we only have the one planet and collecting the data on it is difficult. Whereas in this case, everybody is an independent trial, so we can have, relatively speaking, a tremendous amount of data. So that's something we're working on going forward. The other place that we're hoping to use this is at Aotearoa, which is a lake on the South Island, an old money Lake Forsyth. So this is the Banks Peninsula in Aotearoa, and this is Aotearoa here, tucked in underneath the Banks Peninsula. It is an unhappy lake. You can see the deforestation of its catchment with the exception of a couple of places, and it's had serious water quality issues for as long as anybody's been measuring it, but at least 100 years. And okay, it's got sort of a nice amenable structure in that it's almost a 1D lake, right? It's not really a 1D lake, but it's almost a 1D lake, okay? Its maximum depth is about 1.5 meters. It's very shallow everywhere. The water comes in up here, the water goes out down here, and not much interesting happens across the narrow aspect. So it's almost a 1D lake. Even better, Environment Canterbury has been measuring the water quality at 3 different locations for the last couple of decades. Not at a high temporal frequency, but just about enough. And so one of the things that we're doing is looking for differences between these stations as indications of these spatiotemporal critical transitions. And there's some evidence that it might exist. And this is a project that I've been working on, funded by TPM and with Matthew at Canterbury. And the student who was supposed to be working on it, I had hoped would be here for today, but she isn't here yet. So this is something else we have going forward. All right. So that's about time. I think this is everything I wanted to say, and I need to thank everyone to help get me where we are. So I've already mentioned Pete and Marion and James, and look, I found a better picture of James for you. All right. Okay. A variety of people who've been involved with the BT work over the years: David, Frank, Tron, Alvenia, Alan. I couldn't find a picture of John. My current group and a few of the former students whose work I have pinched for some of these slides: Matthew, Marsden, NHMRC, and TPM. So those are all my professional acknowledgements. My personal acknowledgements, I of course have to thank my family. So Luke and Alice are here, and Claire, and my sister and my parents and my sister's kids. I also very much have to acknowledge my extended honorary family in New Zealand. Thank you all. you will recognize some of these people by their professional mugshots, and they are these wonderful people, but they are also these people. They're much more fun that way. And just in case you thought she was going to escape, no, she didn't. Okay. Well, thank you, everyone.